Hello again, this is Dr. Ali Mugabil and we're doing joint and conditional probabilities. We'll start with joint probability and then we'll proceed with conditional probability. Joint probability. If we have two events, let's say event A and B, like the one shown in the diagram here. If you want to find the joint probability, then basically you want to find the probability of the union or intersection. Let's start with the union. What is the probability of having the union? Which means basically I want to find the probability that the event is either in A or in B. We're looking at this outside circumference. What we're doing here, we're just adding probability of B, and that covers the first circle, plus probability of B, and that covers the second circle. If we just add these two together, like many people do, then what we have done, we have considered this overlap 2 times, while we should have added this only 1 time here. So to remove the duplicate, we're going to subtract the intersection. This is counted twice. So what we are after is the union. And to avoid the repetition, we're going to subtract this term. And this is why we have always here minus the probability of the intersection. So the joint probability for the union equal to the sum of the probability of the individuals minus the term shown here, which is basically the intersection between the two. We can also use the first formula and come up with from the first formula, I can come up with the second formula, which is the probability of the intersection. We basically go from here to here. If we move this term to the left, so probability of the intersection equal to the probability of the sum of the individual events minus. So this formula comes directly from here. Those two formulas are very important to correctly solve joint probability problems. Now, we see from these equations that the probability of the union never exceeds the sum, because this is a positive quantity. Okay, if you subtract a positive quantity, the maximum you can get is probability of A plus the probability of B. Okay, we can write this mathematically as probability of A union B is always less than or equal to the sum, because we have dropped this positive term. And it's going to be exactly equal. When does it equal exactly? If this term equal to 0. And this occurs if they are disjoint, which means they look like this, they are disconnected. So if you want the probability of the union, you take the probability and you just add it up. There is no intersection. So to summarize, in this slide we came up with the 2 formulas for the joint probability. Now, let's now move to the conditional probability. We need to first understand what's the meaning of conditional probability and how it's being written. So when we say probability of A given B or conditioned on B, which means we know that B is already true. It's already valid. It occurred. So according to the formula, probability of A given B is given by the following. It's a probability of the intersection, divide the probability of B. Of course, we cannot divide by a 0 number, so we have to guarantee that the probability is positive. And this is why I am adding here the condition. Let's see now with the Venn diagram, how did we get to this formula? From the Venn diagram, we have the sample space, and then we have A intersection with B. We're showing we're now seeing two events, and we want to find the conditional probability. What happens what's the meaning of the conditional probability? So let's see. Now, if we say that A conditioned on B, which means that P is already true. So our space now, our universe will not be this big square. It's rather going to be everything inside B, because we are conditioned on B. This is our universe. So we want to know what is this probability given or compared to the entire circle. So we know that this is A intersection with B, and that's B. And this is why we divide, when we look at the equation, we look at probability of intersection divided by the probability of B, because our universe now is becoming B. Everything is measured relative to B. Okay? So some would say, what if they are not intersecting? Of course, the probability is going to be 0, because if this is your universe, there is no way you can get A. Or similarly, if you condition B on A, you're always going to get the conditional probability to be 0, because once B occurs, once you are inside the circle, there is no way you can be in the red circle. Okay, so conditional probability or joint probability, they are all true probabilities, which mean all axioms of probability holds true. They hold true for conditional probability. They have to be between 0 and 1 and what have you. All other axioms should hold true. Conditional probability is a valid probability. So let's try an example here to show axiom number 2. Let's make the universe equal to A. Okay, so I'm going to use the same formula in the beginning, same formula we had before here. Okay, and I would love to see to show that axiom 2 is true. So now I converted A to be the universe. I made S equal to A. The yellow square become now our A, and we're saying now what's the probability of S given B, S conditioned on B? What's the probability that we are inside the square given that B is true? No, the answer is automatically 1, because once you are inside the circle, you are already inside the rectangle. We can also go by the formula. It's the probability of the intersection divided by the probability of B. Intersection is going to be, what's the intersection between these two, A and B? It's going to be B. So this is going to be the probability of B divided by the probability of B. This is equal sign, which is equal to 1, because this intersection is nothing but B. And now we're done with defining the conditional probability. Remember that whatever below this line means we are conditioned on this. This is already occurred. This is true. Okay, now it's time for an example. And if we can solve this example, we'll be in good shape. It says here, joint and conditional probability. In this example, we have a box, and inside this box there are resistors. Those resistors could be with the following ohms: 22 or 47 or 100 ohms. Okay, and they also could have percentage of error or tolerance. It could be 5% or 10%. Okay, and in these two lines, we're just looking at the total. So the total number of resistors with 22 ohms is 24, and so on. So what's the question? The question is, it says, we're drawing a resistance from the box with the same likelihood. All resistors are having the same probability of being drawn. And we are defining event A to be drawing a 47 ohm resistance. So event A is defined to be here. This is event A. And then we are defining event B to be drawing a 5% resistor. This is in this side, so this is B. And finally, we're defining event C to be drawing 100 ohm resistance. Here we speak. So here we go. We have C 100 ohm. So now let's ask a few questions. It says find the probability of event A, B, C, and then some intersection, and some conditional. Let's start with the easy ones. What's the probability of having A, or drawing a 47 ohm resistance? It's 44 divided by the total number, which is 100, because in total we have 100 ohms. You can do similarly B. It's going to be 62, and you can also do a C, 62 divided by 100, and C, of course, is going to be 32 divided by 100. So the first part is the easiest part. Okay, now we go to the second part, which is the probability of the intersection. Probability of the intersection is given by the following. Probability of the intersection, we have A intersection with B. It is a 47 ohm, and it's a 5%. So this is clearly seen here. We can highlight this. It's A and B at the same time. So we're speaking of 28. Okay, 28 is the intersection. 28 out of these 100. Now, probability of A intersection with C, they don't intersect, so this is going to be 0. B intersection with C, this is going to be 24 divided by 100. So we got the following numbers, and it should be straightforward. Now, finally, we look at the conditional probability. Luckily, if you remember, we can define the conditional probability. We can find the conditional probability based on the intersection. So probability of A given B is the probability of the intersection divided by probability of the condition B. Don't mix here, it should be the condition. What's the intersection between A and B? It's 28 over 100. This is the probability. What's the probability of being in B? What's the probability of having 5 ohm resistance? It's 62 divided by 100. If you divide these two numbers, we get 28 by this 100 cancels out, we get 28 divided by 62. We can even do it straightforward without going through the formula. So given that it's already B, we know already that it's a 5 ohm resistance, so our sample space is going to be 62. Okay, our total is 62. So now, what's the probability of being, it's going to be A? It's 28 divided by 62 directly, as if we have reduced our sample space from 100 to 62 by knowing it's already in B. So you either do it by the formula or by the definition of conditional probability. We can do the other conditional probabilities. Okay, these are A and C are disjoint, so the conditional probability is going to be 0. Whenever you know it's 100 ohm, it cannot be 47 ohm. We also go for the last requirement, which is probability of B given C. Again, you can do this by the formula, or logically, if it's 100 ohm resistance, this is given, it's a C, which means we are searching in this region. It's 32 total, and I want it to be B. I want to be 24 divided by 32. So that concludes the problem. It helps us understand. There are lots of problems like this where you are given a table and you are asked to find joint, conditional, union, or those sort of requirement. So it's very important to understand how this thing works.